Okay, last time we looked at projectiles with no air resistance, so they'd follow nicely parabolic arcs like this, and we could get a whole lot of information about them. This time we're going to see what happens when there is air resistance, which we sometimes call drag. We launch this guy a little bit harder because it's going to experience all that drag, which I am exaggerating here a bit, of course. Real life air isn't so dense. In this video, we're going to look at the case of linear drag. That's when the magnitude of air resistance is proportional to the speed of the ball, which I've written there as the length or the magnitude of the velocity vector. Notice I've got an m there as well. I think that's a trick I've shown you in the past. It just means the acceleration has magnitude kv, and that makes life a little bit easier when all the m's disappear. Okay. Now, notice I say magnitude. That's really important. Okay, when we did resisted motion previously, we saw that sometimes drag was proportional to the speed, sometimes it was proportional to the square of the speed, whatever it was. Okay, but we've really got to be careful about the direction of air resistance because it's always going against the motion of the ball. And so if the green arrow again represents the velocity of the ball, then the drag is always going to point in the opposite direction throughout the entire flight, and there is no other possibility there. Okay, it's going to be pretty tricky when we change the magnitude of this air resistance, but we'll see that maybe next time. But what does this drag do to the flight of the ball? Well, you can see, first of all, that it's no longer symmetric. Okay, that parabolic shape is gone, and what we'll see shortly is the shape actually approximately follows something involving logs, which might feel kind of weird right now, but more on that later. So the lack of symmetry means that it reached its maximum height actually more than halfway into its flight. I guess intuitively because by the time we reach the downward part of the flight, the drag has already killed a lot of the horizontal velocity, so that means the second part won't get to go as far. So one other interesting thing here is that 45 degrees is no longer the angle that gives the biggest range. But again, intuitively, a slightly smaller angle is actually better because you kind of slightly tone down the time of flight so that the drag has a smaller overall impact, which makes the ball go a little bit further. Actually solving for this optimal angle is rather difficult though, and I won't be doing that in this video. Okay, so we aim to get a little bit more precise with all these things we've been saying. Okay, I want to get some equations going, so let's freeze the ball at some point during its flight and think about what forces might be acting on it. Now I'm saying forces, but what we're going to write down as vectors are just the accelerations, so pretend all the m's have been divided out already so it's not as messy as we were saying before. Okay, because things are going to be a little bit more complex here, we're going to use dot notation and also be super explicit in splitting what's happening in horizontal and vertical directions. So remember, each dot stands for a time derivative, and the double dot means a double derivative, which stands for acceleration in that direction. So, we have gravity pointing down as usual, which would give y double dot a negative g. Then the drag on the ball is always pointing against the velocity vector. So if we put the velocity vector here in green, then the drag must go that way. But because we're looking at the case where the magnitude of the drag is just k times the magnitude of the velocity, that means the drag vector is exactly negative k times the velocity vector. We scale it by k to get the strength right, and then chuck a negative to make it go against the velocity of the ball. So we have something like a similar triangle situation, really, where if we take the horizontal and vertical components of v, which would be x dot and y dot, we could just scale them both individually by negative k to get the horizontal and the vertical components of the drag. Okay, so we can bring those back up to our equations. Okay, this negative kx dot drag is the only source of horizontal acceleration, and this negative ky dot drag is added on to the negative g for the vertical acceleration. And what we get is this pair of differential equations. So for the remainder of this video, we will solve the differential equations to get expressions for x dot and y dot, so both horizontal and vertical velocities. We'll give a couple of physical interpretations of these, mostly to do with terminal velocities and such. Then we could integrate those again to find expressions for the position, the displacement of the ball. But we'll leave that as an exercise for you to do. It's, I think, simpler than it will look if you keep in mind, once again, that pretty much everything except time will be constant there. Okay, so let's go ahead and get the velocity. We could use separation of variables as normal, and by all means try that yourself, but just for fun and to save a bit of space, we'll do it another way. For the x direction, it's a function whose derivative is just negative k times itself. The form of the solution will be ae to the negative kt then. To find the a, we will use the initial conditions again. So when we put t equals 0, the exponential goes to 1, so it vanishes. But at the very beginning, it's the same as the case with no drag. If the ball was thrown at initial velocity u and at an angle of theta, the horizontal velocity would just be u cos theta. So that's what x dot equals when t equals 0. And that tells us that a must just be this initial horizontal speed u cos theta. And we will get x dot equals u cos theta times e to the negative kt. What about the vertical velocity? Well, it's very similar. It's just a non-homogeneous differential equation, so the form of the solution is the same exponential, just with a particular solution at the end there. Naturally, that would be a constant to match the negative g, in which case its derivative y double dot must be 0. So that means we have a particular solution, negative g over k. Add that back in, and that gives us a solution y dot equals be to the negative kt minus g over k. Once again, we'll use the initial condition to get our b. So putting t equals 0, the exponential term is again just 1, so it doesn't do anything. And our initial vertical velocity this time is u sine theta. So that's what y dot must equal when t equals 0. And so adding the g over k gives b equals g over k plus u sine theta. And so y dot must be this whole guy, all multiplied by e to the negative kt, then minus g over k. And that's our velocity equations. Again, these can be integrated for displacement or position coordinates, but I'll leave that up to you to do. So let's focus only on the velocity vector now. And we'll let the ball run its course and see if we can interpret a bit of what we just did. When we did the one-dimensional resisted motion, there was always some kind of terminal velocity, some kind of limiting situation, and in this case we see that the x velocity limits to 0. Alright, intuitively there's nothing keeping it going after the initial boost of speed it was given. So all the drag will just rip out almost all the speed and there's nothing keeping it going. That means if the time of flight is sufficiently long, the motion of the particle will be approaching vertical. Okay, so we could get some sense of limiting velocity by pretty much only looking at y dot then, the vertical velocity. So limiting t to infinity for y dot will destroy all the stuff stuck to the exponential, and that would leave you with the theoretical terminal velocity of g over k going down, which is exactly what you'd expect if the drag kv is to balance out the gravitational acceleration g perfectly, as we have done previously. Very cool. Now, of course, if you don't throw the ball at such a high angle, it might not go as vertical, because this is only in the case where t gets the chance to go sufficiently large. So for a low angle like that, it wouldn't manage to get as vertical. Okay, but what it means though is that no matter what angle you throw it at, when the ball hits the ground, it would do so at a steeper angle than when it was launched, because it would be somewhere on the way to being vertical, even if it's not quite almost there yet. Okay, so that about wraps it up for us here. You'd want to have a go at maybe integrating those velocity functions to get some sort of displacement, and then any further questions we might ask about this would either be actually conceptually similar to the no drag case, something like it reaches max height when the vertical velocity is 0, stuff like that. It's just the algebra's messier because the equations have more stuff going on, okay? Or it might be something numerical or whatever. But that's all for now. Thanks for watching. See you around.